Okay, so hello and welcome to another session of Working with DAMASK. What we specifically want to talk about today is I see that most of you already have run examples, you're already familiar with DAMASK, what it does, how to create some files, run them, look at the global results, look at the local results. Um, we want to go one step deeper. And the idea here is that we want to calibrate the material model of DAMASK, right? What does calibration mean? Do you know about that? So we get a global stress strain behavior from DAMASK simulations, and we know that how our material is behaving. So we have an experimentally obtained stress strain global response of the material. What we want to do is we want DAMASK to give us the exact same global result or outcome, right? When you would have run the previous files, you would know that this depends on the type of geometry that we use. It depends on the size of the geometry that we use. It depends on the loading condition that we use. It depends on the material parameters that we use, right? So when I talk about calibration, what I mean is specifically in the material file. So what are the material parameters that we are using? That would mean I will want to have a very similar geometry or a very similar microstructure in my geometry file that I see for my actual material, right? I will want to apply the same loading conditions that I applied when I tested my material experimentally. So I rule out those things, and now the only thing that remains is the material file and the material parameters there. If my other two things are not correct, although I will identify these parameters, they will also not be correct because my geometry was wrong or my loading condition was wrong. And although I have received a set of parameters, but not useful. Do you understand that? Make sense? Right? So that is his part of the work is, for example, we want to do calibration there. I know we want to do calibration there. I know we will have to do calibration there as well. So that is why we are here. I'm taking a real example. I have not calibrated this before. I will just go with the vibe. We will see how things happen, right? But the thing that I have done here is instead of just manually doing all the work, instead of running a simulation, looking at the global stress strain curve, plotting it in Excel, comparing it with the my experimental stress strain curve, seeing how much difference there is, then manually adjusting the parameters, then coming back and looking at the global response again, see if the curves are closer or farther, and then readjusting. What I've done is I've written a script that does this for me. But you have to understand basically what I'm doing, right? So I will start by showing you the experimental data, then we will come towards the calibration part, and then we will see how we are doing this here and things like this. Make sense? Okay, let's go. So um, my experimental data for the material is here. Uh, so what you will see is I have this stress strain curve, a niobium. Now, you will see that I have stress strain curve which looks something like this. You will see that the stress is just 50 megapascals, and I have 30% of the strain here. Right? You have to understand the history. This test is done at very high temperatures. Right? So the temperature is 1300 degrees centigrades, and this was a compression trial, right? So the applied conditions were compression, monotonic, isostatic as well. So very slow straining, but here we get this, right? So what I want to do is I want to create a representative geometry, right? Which and what we know from the past test, from this test, is that our material did not have a microstructure aligned in a certain direction, so it was very homogeneous isotropic kind of material, right? So that is the kind of microstructure that I will create. Then I will create a load file that applies monotonic compressive load under isostatic conditions, right? And then I will run my simulation and see what does experiment show and what does my simulation result show. And what we will want to do is we will want to adjust the parameters in a way that I get close to
each other.
this curve. You get the point? Okay, good. So for this calibration, I do not need this picture. I need my raw data. Okay, and raw data for this test looks like this, right? The first row contains true stress, true strain columns, and then MPa is written here. What I would quickly want to do is I will just want to move this here. So the first row is some text, and then after that I have data. What you will also see here is that in the beginning I have just the test was just started, although strain is almost zero, but it is in the negative values, right? And it starts to become positive from these values onwards. Do you see that? So what I will also do is, for example, I will just delete these lines to make sure I do not have a problem with negative numbers or things like this that can mess up my equations, right? So 1.5 into 10 raised to power minus 5 is something that I can assume is close to 0. Okay, so this is my raw data file. I will not fix this. What I did is I copied this file to my folder where I will be running the optimization. This is everything that I will be doing there. Let's go to that folder. So what I've done is I have copied this experimental data to my Bayesian optimization folder, and here, for example, you will see these files. Here I have copied this and created a simple name for it and renamed it with relatively simple name, because why not? No? I want to use smaller names. Here you will see true stress is here, true strain is here. You have to see that true stress is in megapascals and true strain is already not in percentages, right? But what we want to do is we want to maybe convert it into percentages later. First, what I will do is I will delete all the negative numbers on the top here, just because they do not make much sense, and we still have quite a lot of data here. Okay, so I will delete this, delete this. Now we are starting from here. To make it simple, what I will do is I will put a 0 here. Can I put a 0 here? Yeah, I can. Okay, interesting. Okay, and then I close it. In the load file, so I will keep the name this, but in my load file, what I need to do is, instead of tension in this direction, I want to apply compression, right? And with 1 into 10 raised to power minus 3, because why not? Another thing that you will see here is that I have commented out these lines. I will just delete them to keep this simple. Did you see that? So I have this commented them out, so they will not run in any case. What I will do is I will just delete them to keep it more clean and clear. Doesn't make any difference. What I now want to do is you saw that I had almost 30% strain, right? What I want to do is I also want to run my simulation up to 0.3 strain or 30% strain. So if I am running my simulation with 1 into 10 raised to power minus 3 deformation rate, and I will run my simulation for 1000 increments, this will be 1, which will mean it will be 100% strain. Almost close to that. Depends on the microstructure, depends on several other things, but yeah, so something like this. Okay. I want to run it only up to 30%. So if I run it for time of 300, that should do the work, right? So what I will do is I will check here how much time I'm running my simulation. So what I see here is I am running it for 1, 2, so 50, 60, 70, 80. Okay. Okay. So that means I have to run my simulation for uh, this, um, this, and this. But wait, what I will do is before I run my simulation, I want to check if everything is working fine, right? So what I will do is I will run my simulation for a very small degree here to check if everything will be running fine, and later we will delete these comments and then we will redo the actual calibration. Okay. Okay. Now so my geometry file is this 15 by 15 by 15 size. It is very small, but it has a lot of grains. So it has more than it should have, ideally more than 1000 grains, right? But even if it has, for example, here it is written that it has a microstructure of 606, so it has almost 600 pixels. Some grains may be represented by 2 pixels, most of the grains will be represented by 1 pixel, but the idea is I have a lot of grains. They are not fully resolved because I am only interested in looking at the global results. I'm not interested in looking at the local results. We have published research papers in the past about this technique. We have shown that if you want to run global simulations, you just want to calibrate your data, all you need to do is run simulations of this small RVE that has a lot of grains, that is a that that's orientation is representative of your material, whose phase composition is also representative of your material. And if you have this and you calibrate your parameters based on that, you will get reasonable results. Okay, so the advantage of this is that the simulations will be much faster because the RVE is much smaller. I can do the same calibration on a larger RVE, it would take weeks. I can do the same here, it would take minutes. No? So the advantage of this is I use a small RVE so that my simulations run faster. I have less data to process so that I can quickly compare results, reiterate, quickly process, right? I think this file is, if not here, you can create your own, or I will also copy this representative volume element with its material file, for example, here in my GitHub repository to give you access to this. For example, you can just copy and paste it and start with it, right? You will also see that I've created this using Dream 3D and then scaled it down by using command geom resize. So your choice. You can do that as well. Now, but this is my geometry file, and then I have my material file, right? So you will see that there is material config.template in front of it because I wanted to give my algorithm option to not run simulations on material config, but to use this to create material config files every time it wants to change some parameters. That is why it has a different name. You can use the same algorithm, you can use a different one. So it has the same things that we talked about in the past. So no homogenization. Some outputs here, for example, I'm just taking F and P as an output. Everything else is commented out, right? You will see that I have commented out all the outputs here, right? And then these are the this is, for example, I have written here aluminum phenopower law, but you can write whatever name you like. For example, NB, niobium power law, right? For 1300 degree, right? And then this is my phase one. Everything is phase one, right? And these are the parameters that are initially defined. Initially defined. These are the ones that we want to calibrate. Okay, how do we do that? Now we will go to the script, right? So if I open this script, what you will see is it is written in Python. What it does is it imports all the libraries. I will be mostly using NumPy for data processing, reading, writing, and analysis. And then, for example, I'm using this SKOPT file for the optimization scheme that I'm using, right? Um, and from this library, different sub libraries to then post process the data and analyze it, right? What you will also see here is, for example, it is already creating an optimization log, and then, for example, I give it an idea of how many parallel jobs to run, right? I can run, for example, 3 parallel jobs. I can run, for example, 5 parallel jobs. It will run all those number of files together. For now, let's make it 1, right? How many number of cores per job? So how many processors to use for each job? Here on this computer I have 120 cores. So let's say I'm using 30. So if my geometry is 15 by 15 by 15, this number of cores per job has to be a whole number that the total of my pixels is equally divisible by. So 15 by 15 by 15 will be something. If you divide that with 30, you will get a full resolved number. So this is fine. If I, for example, use 13, and that is not a whole number, the simulations, instead of getting faster, will become slower, because now it has to shift data every time and it is a mess. Next, we always decide what is the maximum number of iterations. This number of iterations is not for my simulations, but it is for the optimization scheme that I'm running, right? So it will run simulations, compare results of experiment with numerical simulation, right? See how much different it is, how much there is a difference. Then based on that, it will change its material parameters and then we'll run a simulation again. So the first was one iteration, the next one is the next iteration. The more iterations it will do, the more closer it will come to the parameters, right? But we do not want it to run until infinity. So therefore we, for example, can define 20, 30, 50, whatever, right? So what I will do here for this example is I will restrict it to 10. Okay. Okay, so in the optimization scheme, what we do is we compare the error between the experimental results and the numerical simulation results. Okay. What I want to do is I do not want to equally compare all the areas. So for example, I am not super interested in the elastic part. Maybe that can be very different, but I am more interested in the plastic part. That should be quite close or accurate, right? And later you will see that in my optimization parameters that I want to optimize, I've also not provided any elastic parameters. I'm only optimizing my plastic flow parameters, right? And therefore I have created strain segment split, right? I will show you this with an example here, what I mean by that, simulations. And I also need to change it for this optimization scheme. So what you will see here is, okay, so what you see here is that my elasticity is maybe until here, and this is 0.005 is this, so this would be, oh, so this is 5%, that will be 2.5%, right? So strain split is at 2.5%. Okay, and now I am giving weight to the difference below this point and difference above this point, right? So what I say is give less weight to the difference below this point, give more weight to the difference above this point for calibration.
You means that first you have to define the strain. You have to define the strain.
Yes, you will see. I will explain it later. Here it is hard to explain, but just to get the idea, I have split it from here. I say if even the curves do not match here, give it less weight. The curves have to match very well here, right? Therefore you will see that the weight in low range is less, weight in more range is high. That is the only thing I'm doing. Okay, and then this is bias penalty. It basically it learns if the curves are above each other or below each other. So if the curve is above or below, so it knows, do I have to increase the values or decrease the values. That is what it is. Just use 5. Maybe you can play with it and change this later. Combined objective weights. So what I have also done is, instead of just looking at the stress strain curve, what I do is I transform this into a hardening curve as well. So delta stress by delta strain, and that is also more sensitive, right? What I do is I compare my experimental hardening curve with simulation hardening curve, and what we want to do is we also want to compare them, because we do not just want the curves to match, we also want their slopes to match. So that is a better matching comparison, that is a better calibration technique. So that is what I've done here. And here it asks how much weights do you want to give. So I've given them 50-50 weights. So hardening and stress strain curves should match well. I can also say, oh, curves should match, hardening rate I don't care, or hardening rate should be very good, curves I don't care that much. Make sense? Here I have given it 50-50. And then, for example, hardening parameters. So when we have experimental data, because the data is not very smooth, it is always not very smooth, we will see, and therefore sometimes we need to smoothen it a little, and these are all the parameters for that. Don't worry about them, we will again talk about them later. Here I'm picking up the files. It creates some folders for me. It picks up this material config template file, geometry file, load file, and database file, which is my pure nb.txt. Remember this, right? So that is what I'm picking. In my material config file, I am defining this parameter space that needs to be calibrated. You can remove some parameters from there, you can add some parameters here, do whatever you like, right? But the thing is, the name of the parameter is given here. Its lower, its minimum level, its highest level is given here. So it will always try to optimize it between this window. Make sense? So for example, if I want to identify what should be the value of the hardening parameter, that is what I want this to find out for me.
These parameters are different from material file. In my material file, we don't have these files. I have to change them, yes?
If you have, if there are different parameters in your material file, of course you have to rename them.
Because completely different.
Yes. If you will talk about Damask 3, you will also have to maybe change the script a lot as well, because later you will see when I am running Damask simulations, the script that I use for 2 that I've already shared with you is something that I'm using here for Damask 3. Maybe you will have to change that as well. But the optimization scheme, the methodology will still remain the same, and that is why we are talking about it here. So this is my parameter space, which means, oh, I want you to find the hardening parameter value, but between these 2 points. So not from minus infinity to plus infinity, but between these 2 points, find out which value will best describe my material. So it will always play within this space, right? That is why you will see a low and a high,
Yeah.
right? So minimum value, maximum value, it will always play between this. It will never cross these boundaries. And this is required for the optimization scheme. So if you will remove any of this, it will not work. So it will say, oh, I need this value, otherwise cannot find anything, right? Then what I'm doing is it is just checking if everything is already available there. It clears up the previous files, and then it starts the simulations. The important thing here is, for example, this is how I am building up my material file. So it starts this test, then it creates a material config file based on what it learns from an optimization scheme. Later in one of the functions, it writes all these values there, creates a material file, right? By changing those values, those numbers in the material file. We will see that later as well. Then it runs this Damask simulation, right? You know this. So Damask spectral, this, it will run them, it will calculate.
Now, based on this script, now, especially working with material file. First, apply it, the Python codes for changing the material file.
Yes.
After that, with this new material file, go to this DAMASK simulation.
Yes. So what I've done is, what you will see is, Again, we will see. But what it is doing is it is creating it, then post processes it, looks at the stress and strain, compares it with my experimental stress and strain data, sees how much error there is, then based on this learning changes my field of parameters, set of parameters, creates a new material file, runs that simulation, looks at the global stress strain, compares it, sees if the error decreased or increased, and then onwards it goes. Okay, makes sense? That is basically what it is doing. And below this, what I just want to do is experimental strain data. I just have to see because my strain here is not in percentage, but the strain that I'm calculating here is, right? So either I do not convert this into percentage or I convert that into percentage. So I need to have, and of course if this is in megapascals, that should also be in megapascals. So my stress is the same. This is also in megapascals. And the stress in my file, the material file, was also in megapascal, so that is fine, but this is not fine. So either I remove this, or I when I'm reading my data here, not here, my data was read somewhere earlier. uh, 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 uh. Where? Here. Yeah, so this is where and again you have to check, sure, what is your delimiter, what is your header that you have to skip. So my top line is something that I wanted to skip, remember that, because there is no data there, it is just for me to understand what is stress, what is strain. My first column was stress, my second column was strain, that is why you will see read this and read this, and here I just want to do 100. So now it will automatically multiply everything with 100, and then now it will be converted into percentage. That is all I want to do until now. I want to put it on the side. I want you to remember this, okay? And we will run the optimization scheme. We will see what we get. Open in terminal, and I hope the simulation runs. So what we will do is Python 3 optimize and run this, right? So what you will see is, let it first run and then I will share. Okay, so it's running. So what it did is, according to this script, what it did is it copied this file, geometry file, load file, and the modified material configuration file. So it changed these parameters in it, and then it pasted them here. Okay, and if I will open up this material file, you will see these are the values that it wrote here, right? And now it is running simulation on this material file. Make sense? And what it will do is, once it will finish, it will do the post processing. It has already done that. In the post processing, I will get my stress and strain, right?
Question happened for me before this. Now we applied geometry file, loading file, and for material file.
Hmm?
You told me it refers to the new material file. What's the new material file? We have one material file. We are going to optimize it.
Yeah.
Now, therefore, one material file, I have it. I have to apply, and we just have a curve or maybe data, just string curve. How to apply this?
So in my initial material file, let me go back. So the material file that I gave it here, this is its template. This is the template, right? And I have told it in this Bayesian optimization. Where is my field that I am playing with? So I have told it in this here that use this template, but for these parameters, g dot not slip, n slip, tau not slip, tau sat slip, a slip, h not slip, right? For these parameters, change them between this and this to find out the best parameter that will give me the global results that are equal to my stress strain data, experimental stress strain data. Therefore, what it will do is it will use this template. Then first it just needs to run some reference simulations, 3 or 4 reference simulations. So it will just randomly change these values of these parameters within this space, run simulations, collect data, see what was the error, and from there learn. So what happened when I increase this value, what happened when I decrease this value, how are these parameters independent, it will learn this. And then based on this learning, it will try to it will try to write parameters in a way that my error becomes minimum and minimum as much as possible.
For me, I mean that automatically read it. For example, I have to this file, automatically read it, and try to start to
Yes,
optimize.
that is what I was showing, right? So this is my template. What it is doing is in all these runs, what it is doing is it is changing the material parameter file values, and it is trying to run those simulations and compare the results. Okay.
Yeah.
So if I will open each of these folders, all these folders are for run 1, run 3, run 5, run 7. They all have same geometry files. They all have same load files. The only difference is
Material.
the material file, the only those parameters that I defined have now different values, and it is running simulations, and based on them it is learning. Okay. Hmm?
With the modified material file which we got from the optimization script, if we run the simulation again with the modified script, will there be any changes again?
Which modified
Like
script?
now once after simulation the material file has been changed.
Yeah.
So with the change material file, if we run the simulation if we run the comparison simulation, will we get the another material file?
No, you will get exact. We will see. We will see. Wait. You have to understand. So remember this. Remember what here. Remember this. We said maximum iterations 10. Therefore, it will run 10 simulations, and after that, if I will look at the results, it will say, oh, I have completed everything, and then based on them, I have done evaluation of 10, and based on that, these are the best set of parameters that you can use. What I have done is, for example, best parameter, it will also write out the best parameters, but not good enough. We want to see the results. No? So the results are written here. That is what I want to look at. So what you will see is, huh?
The scale of
So experimental stress strain data is this one, and simulation is going here. Ooh, interesting. Experimental hardening rate is this. I don't know why. And simulation hardening rate is this, right? So what I already see is that the parameter space I have defined is not good enough, right? So the error that I am having is 1750%, quite a lot, right?
Because the experimental data refers to 300 degrees, but we don't define temperature for loading file. I think that it
Wait, wait, wait,
differs
wait, wait,
with
wait, 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 wait.
it's thermomechanical.
No, we are just running isothermal simulation here. Let me. So,
Problem is,
all your questions are good, but too fast. Slow down. First, I want to do is what I want to do is I want to bring them in a reasonable window
yeah,
of collaboration. What I know is that tau not slip and tau sat slip are the values that control the initial slipping and then how the hardening from there evolves. What I will do is I will bring them down to a very small number, 1e4, and I will reduce them to a very small number as well. Okay, and what I want to do is I will want to run this optimization again. So you saw what I did here, right? So I saw that the difference between the area in which my optimization scheme is trying to find the parameters, the window of that is defined to be very high, and even though there is a large gap, it will not break that window and come down. I have to manually adjust that window, right? And now what you will see is, oh, the error is significantly large. I have to bring down all the values to a very small number. H not slip 1 E3 1 E5 N slip is 0.1, high is 2, and then I will save it, and then I will want to 0.01, and I will close this and I will run it again. So what basically that is why I said it. So even though you will see that it seems automatic, but you still have to tell it its limits, and you can only do that by looking at your results, seeing what it is doing, what you're getting, and then define this window where it nicely plays. So you will see. So now what I've done is I have defined this whole parameter space with very low numbers, and now we will start seeing maybe some results. Another thing that is happening here is that oh, I did not delete my results earlier. Another thing that is happening here is that my I wanted to say something. The load file that I've defined is only for up to 5% of the strain. So I'm still not comparing my whole stress strain experimental curve with stress strain numerical simulation curve. For now, I'm just trying to find this space. And that is how you can save some time. If I would let the simulation run for maybe 1000 iterations and then get the same outcomes, not a very good idea, right? So first I am just optimizing my time, running quick simulations in a very smaller window to see if everything is working fine, and later I will remove those comments. I will let it run for a larger number of increments, and then the data that I will get will be the errors that I will get will be for the whole curve. For now, they are just for the small part that it is comparing. Let's see what we get this time. What I want to do is I want to delete all of them just to get an idea. I don't know which run is this. I think this was delete this. And now you will already see that it is taking some time to converge, and I don't know why. In which space is it working? Okay, converged. Okay, so now we have, so now my experiments are here, and my and my simulations are here, right? So now the material is extremely soft, and yeah, also not very good. But what I want to do is I want to see if it can find its way up somewhere. We will see in the next simulation. Okay. And what you will also see is that I have this data at the end of my experimental file, which is being plotted here. See this? What I want to do is I want to remove this as much as I can. um, and then we will see. Oh, it is still no. Oh, it is still in a very narrow range. Oh no, but it is 1e4, 1e4, 1e um, 1e5, 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 1e7, 7, 7, and then I control S, I close this, I stop this, I want to delete this and this and this, and I want to run this again just to do a clean start. And what I'm doing is I'm trying to find this space here so that at least my first stress strain curve is in a range, so that later it can identify where it wants to go. No? Um, okay. Okay, so my stress strain curve right now is this. Not very good. And the parameter range that it chose was tau sat slip and tau. So all this was 10e6 in the middle of this. Now, so I know I have to make it 1e7, 1e7, 1e9, 1e9, 1e7. I will close it, I will stop it again, and I will run it again. And I just have to run it again because when I change this state, the program that is running in the past is just using the old script, and I have to stop it and run the Python program again if I change something here. What I also have to always be very careful of is that I am always saving, pressing Control S on when I make these changes. Otherwise, the new script will not know that. Okay, so what we get now is this, and now it used tau sat slip and tau not slip values of 3e8, 8e8, and 8 is too much. So what I will do is e6, 5e6, 1, 5e7, 5e7. So close this again, saved it. What I will also want to do is I will now want to run it for a slightly larger, longer strain. So I remove these two. Let's see what we get now. The run will be 6 or 7, I think. But if I look at these results, so too high. No, too high. Now it is running up to 670. Maximum number of cutbacks exceeded. Wow. So it was not able to converge. but we will still see results. And if I look at them, they look something like this. No? So now you will see that my experimental stress strain curve is this blue one, and my simulation stress strain curve is because my other space is not right. So wait, I have to check. Hardening. What I will do is I will use the default values here. So the default value of g dot not slip is 0.01, so 0.001, 0.0001, 0.0003. The n slip value is 20, and here I've defined it to be 15, 25. This is now correct. A slip value is around 2.25, 1 and 2, and H naught slip value is close to 75 E6. 1 E6, 1 E7. Okay. Let's delete everything again. And now run this to see what we get this time. But another thing that you can do, for example, in the for your cases, is not to play with the parameters like I am doing, right? So if I will spend like 20-30 minutes, I will still know what I'm doing. I will be able to quickly check with what I know from the past, what every parameter is doing. When you are starting, a good starting point always is to find the set of parameters from literature and use that as the center line, and then add 15% of the values on the higher side, 15% lower values on the lower side, and then use that as an initial space to see how much is the difference, and then run some iterations, see if the curve was getting closer, but it did not get further close because on the graphs you will see all the parameter values are written, and then you see, oh, because this was the highest value of this parameter, then maybe you can extend its window a little bit more. And if you are already going in this direction, maybe you can shorten this window from the behind a little bit more. So the idea is you run the optimization scheme in a very close window and let it find its parameters, right? So the best idea will be to identify some parameters that are available in literature for a similar material, use that as a relative idea of which would be my parameter space, use them here with a lower window and an upper window, and then let the optimization run and find its results. Let's see what we get now. Okay, so you see now we are getting elastic part, right, and the plastic part, right? So they are quite close. What you will see is they are not as they are not even close because of the elastic part, and you know that I am not optimizing my elastic parameters. Hmm? Um, so that is why I have to define my elastic parameters in the material config file. Those, for example, for my case are defined here. How do I identify them? So this is quite easy. How do I identify them? I look at the slope of this line, right? So this is my experimental data. I look at the slope of this line. You can find the slope from anywhere you like, right? From this slope, what you will do is you can use formulas to convert Young's modulus or modulus of elasticity into C11, C2 to C44. C11, C12, C44. There are formulas given. If you will need help, we have published research paper. We republished these formulas from a book that we took for easy use. So you will plug in the values of modulus of elasticity and Poisson's ratio of this material, and you will get C11, C12, C44 for the material. If I will do that calculation, put these formulas here, you will see that this slope will be quite close to what I am getting here, right? So for example, the case, you do not have to calibrate them. It will take too much time. You just calculate it, plug the exact right values here, and everything should be fine. Okay, that is what I will want you to do with this file later. But while we are at this topic, what you will see is I am running my simulations until this point. So I'm still not running my simulations up to 50% of the strain, or the experimental data correctly was presented up to 30% of the strain. So I'm not running my simulations until this point. I'm just running my simulations until here. You get the idea, right? So I have to run my simulations until this point to get a reasonable comparison. But if I look at my other results, what you will see is, so what you will now see is that it is changing these parameters, and based on that my stress strain curve is shifting, right? And based on that is calculating the error, and what you will see is that here the error was 30%. Then when it changed these parameters, this error dropped to 25%. And then it changed other parameters again, and the error increased more than 30%, right? And what we want to do is it will automatically continue to change these parameters and minimize this error. So it will learn through this process. Okay, and that is what parameter optimization is. Um, do you have any questions from this? I think my simulations are still running. Yeah. I think you will have a lot of questions when you will automate when you will use this for your own case and you will want to calibrate your parameters. I will want you to to do this parameter optimization and calibration smartly, intelligently, by knowing that the data only until 30% of the strain is correct. After that is not correct, right? So remove this data from the file. Just use data from this point until this point,
30%
right?
strain hardening I need to I need to
Until up to strain, and then also run your simulations up to 30% of the strain as well, right? Identify these elastic parameters first, so the curves at least here match quite well, and then adjust these parameter spaces in a range so that it tries to I think the parameter space right now is quite nice, so it is already in this range. And once your elastic parameters will be adjusted, once your plastic parameters, it will start identifying this window itself. Just let it run, see which windows it is already hitting, right? So for example, I see here 2E7 tau not slip is, if I look here, tau not slip is, I have defined this window to be 5E7 and it is going up to 2E7. It is saved. Yeah, so see if, for example, in these parameters maybe you're hitting a window on the positive side or on the negative side, and that means, oh, optimization tried to find solution here, could not, and then came back. Try to increase that window in that direction and see if now, if it goes there, can it find out parameters there. It is still not, you will see, it is still not fully automatic. You will still need to define its boundaries. You will need to adjust certain parameters, but it does a job pretty well later. So if that is designed nicely, I want to show you some. Wait. I want to show you some results from the Bayesian optimization that I ran previously. And for example, here are the plots. So I will show you these results. So I ran this, you will see, for 100 iterations, right? And here is my error window, right? So I had to define these windows again after multiple attempts, and what you will see here is that my hardening error was less than 25% and my stress strain error was almost 5%, which is quite low. You will see, I want to share what it looks like as a stress strain curve, right? So these are all the data that I obtained. So this is my matching stress strain curve and this is my matching hardening curve, right? And then you will see, now see this parameter space and see how these curves shift, right? So it is changing its parameter space and it is trying to find parameters that give me minimum error. See that?
Yeah.
Right? So that is what basically optimization is doing. What we need to do is we want to put it in a very narrow window and then run it to see which parameters will give me the best result. So the slope is okay, the hardening, the overall stress strain value is okay, and everything is fine. If I will get a very large window, that is what I started here from. It the shift in the curves will be very large because it will try to look at the value here, look at the value there, and of course the shift will be very large, right? From there you can maybe narrow down, okay, this is the parameter playing area for this parameter from here, but you will see some examples now. So if I keep showing you, so these are, now you will see these are the bad results, right? So from this is where it was learning. Now so you will see the slope is different and therefore stress strain curve is different, hardening is different, and at the more I go backwards, the more you will see that it was trying to find out the area, and from this basically it was learning everything on what it should do, right? And the more forwards I go, right, what you will see is that close to, so this is very, in the very beginning the curves were all over the places, for example, not a very good fit at all, right? But if I go to, for example, run 100 now, so from there it tries to find out this very nice parameter space with minimum error, and from here you can choose which curves match do you like most, and you can pick up that material file with those set of parameters and you can use them for all your next simulations. Make sense? This is what we are looking for, aiming for, that this is what that script is written for, but you can use that, modify that, play it for your own case. But I had to do all these things, clean that data, run simulations up to the similar amount of strain, and all these things in that case to then get a good fit and comparison. That is what I want you to do here. If we quickly look at these results further, maybe we have better results. So yeah, you will see that it saw that, oh, I did something, I changed these values and the error jumped to 60%. Oh, the other parameters were correct, so it came back, right? So that is what it is already doing. So this was the big error, and now this is the smaller error. You will see that it is trying to keep the curves as close as possible, but their shapes are not right because this elastic parameter is not correct. My parameter space might not be correct, so it is already hitting the upper or the lower windows, and that is why it is behaving like this. But you get the idea. Okay, so I will put this file. So I've already put this file, the Bayesian optimization DAMASK 2 file, in my GitHub DAMASK repository, which is public. I will put this geometry file and this material template file, but you will have your own material template file. So it should also have all this phase information and texture information in. For this, you will have your own. Just use them, create your own load file, run this optimization scheme, and find out the parameters. Okay.
One point
Hmm?
for elastic parameters will be constant because
Yes. Yes. Yes.
changed, but the plastic parameters will be changed.
Yes, that is why we do not want to optimize elastic parameters. We want to find out their values from this slope and just put them in our material file template.
Constant because in the material file. But for plastic,
Hmm. Okay.